Okay, so we are going to start off with this topic, concept of capacitors and its principle. So we are going to understand how a capacitor works. Okay, what is a capacitor and how does it works? Now, what we already know is that if you provide charge to a conductor, let's say this is your conductor, and if you provide some charge to the conductor, what will happen? This conductor will develop some potential, and this potential that will be developed is 1 by 4 pi epsilon naught charge given to the conductor over the radius. You already know that the charge and the potential developed by the conductor is proportional to each other. This you already know. In the previous video it has been explained. Now the problem is that if you give a lot of charge to the conductor, it will also develop a lot of potential. More charge, more potential. And a lot of potential, that is a very high potential on the conductor, is not desirable. It is not desirable. That means a very high potential is not something which is desirable. It is not good. Why is that so? Because you already know that a potential developed on a conductor will also be proportional to the electric field. That means if the conductor has high potential, it will also has a very high electric field. You also know from the previous chapter that the electric field on a conductor will be is equal to sigma by epsilon naught. This you have known from this infinite sheet derivation. I hope you all remember the infinite sheet derivation, that the electric field will be proportional to the charge density. Now, if you keep on increasing the charge on the conductor, the charge density will also increase, the potential will also increase, and as the potential will increase, so will the electric field will also increase. And a very high, that is a very strong magnitude electric field is established. Now, when a conductor holds a large amount of charge, its potential is also high, and associated electric field becomes high enough. The atoms near the molecules, atom or the molecules of the surrounding air get ionized. If you have a very strong electric field near the conductor, a very strong electric field near the conductor will ionize the atoms and molecules which are nearby. I hope you know what an ionization means. For example, if this is a molecule, so because of being a very strong electric field, this electric field is going to attract the negative charge of the molecule, and eventually this what will happen, the electron will be taken off. Electron will be taken off, and this will eventually become a positive charge ion. So by this, what happens is, because of very strong electric field developed by this conductor, will ionize the air around it, will ionize the insulated medium around it. The atom or the molecules of the surrounding get ionized. A breakdown occurs in the insulation of the surrounding medium. Insulation of the surrounding medium means if the medium around the conductor is insulator, even though the conductor around this, even though the medium around this conductor is an insulator, because of very strong electric field, because of very strong electric field, the insulating property will also break down. For example, air, the breakdown occurs at in the order of 3 into 10 raised to 6 volt per meter. You may have discussed about this lightning. So lightning takes place when the potential difference or the potential in the cloud is more than 2 lakh volt, 3 lakh volt, like that. That means for a very high potential difference, even the insulator would break down. Even the insulating property of the surrounding medium, this will break down. Okay, because of the very high potential developed on the conductor or very strong electric field. So that is the reason why a one single conductor, if you keep on giving a lot of charge on this conductor, if you keep on giving lot of charge to this conductor, it will develop a very high potential, and it will also develop a very high electric field, which is not desirable. You don't want this. And because of this very high electric field, insulating property of the surrounding medium will break down. Now, because of this all issue, this is why one single conductor cannot hold a lot of charge. You already know from the previous video that 1 farad is a very large amount of very large unit. And being a very large unit, it will have the conductor to have 1 farad of capacitance. The radius will be in the order of 10 raised to 6 kilometer that we have done in the previous video. Here you can see that if there is one single conductor, you cannot give a lot of charge. Then what should you do? So what should you do? If you take one conductor, and provide positive charge to this conductor, it's pretty simple. If you provide positive charge to the conductor and bring another conductor near to it, this is supposed to be the neutral conductor. Because of electrostatic induction, negative charge would accumulate on this side of this conductor and positive will accumulate here. And if you then do earthing of this conductor, then electron from the ground would come and neutralize these positive charge. Electron from the ground will come and neutralize these positive charge, and these positive charge will go away. This positive charge will then go away. Now, because this conductor was positive charge, so obviously it will develop a positive potential. And now this conductor is negative charge, so it will develop a negative potential. If you consider the system of both these conductors, together, then their net potential, their combined potential or net potential will be the positive potential and minus the negative potential. Basically, you will have to subtract these two, and both of them net potential will then become almost is equal to 0. Not exactly 0, but almost next to 0. That is very small value. Now, very small value. Why very small value? Why not exactly 0? Because the induction of charge, let's say the charge on this plate was Q. Due to induction, it is not possible that exactly negative Q charge is going to accumulate here. Because of the induction, a negative charge will accumulate, but not exactly negative Q. Might be a bit less. And that is why this negative potential is a bit less in magnitude compared to this positive. And that is why when you add them up, it does not equal to become 0, but almost very small value. Now, what is the use of doing this? What is the use of having one conductor, another conductor, then earthing it? We know that Q is equal to CV. That means C is equal to charge over potential, we already know. And if this potential decreases, then the capacitance or ability to hold charge for a unit value of potential increases. So this capacitance is going to increase if this potential is going to decrease. So effectively what we have done, that we have two conductors, one positive, another we have earth, will develop a negative, and both the conductors, if they are taken as a system, then their net potential would decrease to a very small value, and thereby increasing the capacitance or ability to hold charge will increase. Okay, this value, C value, will increase. So what do we understood? We understood that the capacitance of an insulated conductor is considerably increased when we place an earthed connected conductor near it. Okay, the capacitance, the total capacitance will increase if we keep an earthed connected conductor near it. Then we will now go through what is a capacitor, because what we have understood is a capacitor, how to build a capacitor. You see, the system of these two conductors is called capacitor. I have explained it before that capacitance is a characteristic, it's an ability, it's a property, and capacitor is a device, as in resistance. Resistance is a device, resistivity is a property. Okay, like that, capacitance is a property, it's a characteristic, and capacitor is a device. Okay, it's a system of two conductors. So how do you formally define a capacitor? Capacitor is an arrangement of two conductors. Mind it, arrangement of two conductors separated by an insulating medium. Obviously it has to be an insulating medium, because if one of the plate or one of the conductor is positive and another conductor that you have kept here is happens to be negative with an earthed one, if you keep a conducting medium between them, if you keep a conducting medium between them, then obviously these positive charge will move and neutralize the negative one, and this negative will again neutralize. So these two charges will get neutralized. So that will be no sense of keeping a conductor in between. So what you have to keep? You have to keep an insulator in between. Okay. So arrangement of two conductors separated by an insulating medium that is used to store what? Store electric charge and electric energy. We know if electric charge is stored, then electric energy is also stored. So capacitor is a device to store electric charge and electric energy. Now, a capacitor in general consists of two conductors of any shape and size. Any size and shape means it can, the capacitor can be like this also. This two randomly non-symmetrical conductors can become capacitor because it is given. You see, it is any shape and size. So shape and size can be a variety of different shape and size of the capacitor. In this chapter further you will learn about different types of capacitor, like a parallel plate capacitor. This is a parallel plate capacitor. You may have a spherical capacitor where there are two conductors like a concentric spheres. You may have cylindrical capacitors, again concentric cylinders. Okay, many different types of capacitors, and but they all have the same thing, that it has to be two conductors of any shape and size and carrying different potential and charge. Okay, so both the capacitors must have the different potential and charge. Both of them should not have the positive charge or not having the negative charge, one of them positive, one of them negative, and placed close together in some definite position relative to each other. This point is also important. Definite position relative to each other means that the two capacitors or the two conductors is not necessary that they has to be placed like this. You can place it like this. We can place it like this. If you have two conductors, you can place it like this, because by the definition itself it is said that close together in some definite position relative to each other. Definite position means position not changing, their positions are is constant, and relative to each other. Okay, pictorial representation of a capacitor. So capacitor is drawn like this, as you have a resistor which is drawn like this. This is a resistor. So capacitors are simply drawn like two parallel lines, like this is a capacitor. This is a variable capacitor. Okay, this is a variable capacitor. A variable capacitor is the one where the value of capacitance can be changed later on. Okay, the value of capacitance can be changed. Now look at this figure. Say here you have two conductors. One of the conductor has a positive charge upon it, another conductor has a negative charge upon it. Obviously, the first conductor will develop a positive potential. The next conductor is going to develop a negative potential. So a capacitor consists of two conductors having the charge plus Q and minus Q, plus Q, minus Q. The potential difference between them is what? The positive potential minus the negative potential, because you're calculating the difference. Okay, positive potential minus the negative potential. Here Q is the charge on the capacitor, and note that the charge on the capacitor does not mean the total charge given to the capacitor. That means if I ask you what is the charge on the capacitor, it does not mean this plus Q and then minus Q, because if you do the plus Q minus Q, you are going to get zero always. Now, whatever be the magnitude of the charge on one of the conductor, the same magnitude opposite sign charge will be there on the other conductor. So if you do that, you'll always get zero. So charge on the conductor is considered as Q, only this value, the positive value. Negative value is not taken. So charge on the conductor is only taken as Q, not as plus Q and minus Q together, because that will always become zero. That means your the total charge on the capacitor will be Q, and again you will get the same relation that the charge Q on the capacitor is proportional to potential difference. Now the charge Q on the capacitor is proportional to potential difference between the two conductors. Mind it, when we did the isolated spherical conductor, in the previous video you can see the isolated spherical conductor. There we calculated the capacitance to be simply Q by V. Q was the charge given to the spherical conductor and V was the potential on the conductor. But that was one single conductor. It was only one single conductor and you were giving some charge to the conductor and some potential was developing. But here we are not having one single conductor. We have two conductors. We have a positive and negative two conductors. So now this formula, that is Q is equal to CV, the V here will become the potential difference, not the absolute potential of one of the conductor, but rather potential difference between the conductor. Potential difference between the conductor. Okay. So finally, your capacitance value will be Q by V, and V here is the potential difference. C is equal to Q by V and V is equal to potential difference between the two conductors. This is very important because you will get a lot of questions for JEE mains level questions. You will get where you have to calculate the capacitance of system of conductors or system of conductors, where you have to calculate the potential difference between the conductor. We'll be doing a numerical soon. Then you will get this through that it's not the absolute potential of the conductor, but the potential difference between the two conductors, which is taken to calculate capacitance. Very simple. So the capacitance of the capacitor may be defined as the charge required to be supplied to either of the conductor of the capacitor, so as to increase the potential difference between them by unit amount. So here also you see by the definition again potential difference. So whenever you have an isolated single conductor, there you take V as the potential on the conductor, and if you have two conductors, then you take V as the potential difference between the conductor. The capacitance of a given conductor is a constant. Okay, it's a constant and it depends upon what? The geometric factor. Again, we have done this before, that the shape and the size of the conductor decides what the capacitance is going to be. Okay, and relative position between the two conductors. And the last thing is this nature of the medium between them. This nature of the medium, we already know this nature of the medium should be an insulator. Okay, but what kind of insulator? There are many different types of insulators. Some has higher insulating property. That means the insulator also you have done it as a dielectric. Okay, dielectric we have done previously, dielectric, and we have already done that dielectric constant or relative permittivity is also dependent upon the electric field and the polarization. I hope you remember this expression. So again, what is the nature of the medium that you have kept between the conductor? For example, if you have a parallel plate capacitor and if you have kept a medium in between the plate of a dielectric constant, that is ER. Okay, so that also is taken into account. Okay, so we are now going to do this parallel plate capacitor. We are going to find the capacitance, that is the value of C, or basically the expression for C for a parallel plate capacitor. Now, till now, if you still have any confusion regarding the capacitance, the conceptual part of the capacitance, or why are we earthing this, okay, this earthing thing, why are we earthing one of the conductor, and how the potential is getting decreased and capacitance getting increased, any part, if you have any confusion, go back to the video and see it again, pause it, see it, write it down in your notes. It takes some time to settle down in your head. These concept will take some time, so don't watch it in one shot. Repeat the video once or twice. If you are confident enough that you have understood the whole concept, then you can move on to parallel plate capacitor. Now a parallel plate capacitor, for example, let's say if you take a parallel plate, so how does it looks like? First, let us see what does this parallel plate capacitor looks like. So if you keep the two plates and you look at them from side, say if you look at them, then it will look like this. One of the plate would be a positively charged plate. Okay, this will be a positive charge plate, and the other plate will be a negative charge plate. Okay, one of the plate again will be earthed also. Okay, this will be earth also, and this same thing from this side view, it looks like this, and the front view, if you look, it will look like this. This will be the positive charge between the negative charge. This value here, this is the area of this plate. Okay, area taken as A, and this here is the distance between the plate. Okay, so this is how a parallel plate capacitor looks like. So D is the distance between the plate and A is the area of the plate. Now, if you have two plates, one of them positive and the other one being negative. In the previous chapter, you have done that a positive charge infinite sheet is going to make an electric field. Okay, this infinite sheet is going to make an electric field, and the value of this electric field was sigma by 2 epsilon naught. The value of this electric field was sigma over 2 epsilon naught. What is sigma? Sigma is the charge density of this plate. What is sigma? Sigma is the charge density. So sigma is the charge density of the plate. The positive plate creates an electric field, that is sigma by 2 epsilon naught. Negative plate will also create an electric field which will be pointing towards itself, and that electric field will also be the same, sigma over 2 epsilon naught. As you can see, the positive plate electric field, that is green in color, in the same direction as the negative plate electric field, red in color. So the total electric field or the net electric field in between the plate positive and negative, the net electric field will become sigma over epsilon naught. You basically have to add them up, sigma over epsilon naught. Now to calculate capacitance of this plate, we need two values. We need charge and we need potential. So let us now find the charge. Let us now focus on this charge. What is the charge on the plate? What is the charge Q on the plate? The charge density of the plate is sigma. We already know that. That means the total charge on the plate is going to be the charge density sigma into the area of the plate. Sigma is the surface charge density. and A is the area. So if you multiply the surface charge density with the area, you are going to get the total charge on the plate. Next, we are going to find what is the potential difference between the plate. What is the potential difference between the plate? Remember, we just now did that this value V is not the potential of one of the conductor, it's a potential difference between the positive and the negative plates. Now, in the previous topic, that is potential, you have done this that E is equal to minus of dV by dr. And this was the potential gradient. Potential gradient. Now, this can also be understood as E dot dr is equal to dV. Or dV is what? dV is the potential difference, delta V, and dr is the distance between the 2 points. In our case, one of the plate is positive charge and another is a negative charge, and I want to know the potential difference between the plate. So if I want to know the potential difference between the plate, I can simply find it by multiplying the electric field with the distance between the positive and the negative plate. In our case, the distance between the positive and the negative plate is D. Distance between the positive and the negative plate is D. So potential difference for us will become the electric field into the D. D is the distance between the plate. And what is the electric field for us? We have done this. The net electric field between the plates is sigma by epsilon naught. That means my potential difference would come to sigma over epsilon naught into D. My capacitance value, which we found out, capacitance will be Q by V, and Q is sigma times A. That is total charge is equal to the charge density over times charge density times the area of the plate divided by again sigma by epsilon naught into D. These two sigma cancels and you will finally get epsilon naught A over D. Epsilon naught goes to the numerator. So this is your capacitance of a parallel plate capacitor, epsilon naught A by D. As you can see, the capacitance is directly proportional to area. Greater the surface area of the plate, more will be the capacitance. More capacitance means more ability to hold charge. It can hold more charge. And capacitance is inversely proportional to D. That means if the plates are very closer, if the two positive and negative plates are very closer, then it will have a very high capacitance. You keep the plate further away, its capacitance is going to decrease. So very well we can figure out if the plates are brought closer, the capacitance increases, and if the plates are pushed away from each other, then the capacitance decreases. Another thing is the medium between the plate. This medium between the plate. Now what happens if I introduce a different medium between the plate? Let's say if I have this plate, positive and negative, I introduce another medium between the plate, which is some kind of dielectric, some kind of insulating medium. You know, insulating mediums are dielectric basically. So if I introduce this, the capacitance will then become epsilon R, epsilon naught A by D. Capacitance is going to increase. The capacitance is going to increase by this value of epsilon R, that is relative permittivity or dielectric constant. So if you introduce another medium between the plate, which is a dielectric, then the net capacitance again increases. So how do the capacitance increase? Number one, by area. You can increase the area. Number two, you can decrease the distance. Okay, decrease distance. And number three, by introducing a dielectric between the plate. Okay, by introducing a dielectric between the plate. So these are the three factors upon which the capacitance of a parallel plate capacitor depends upon. This is a very easy derivation. Please go through this again. This is a standard CBSE as well as PU board derivation. Go through this. Okay, very simple. And then we will be doing numericals on this topic tomorrow.